In the name of Almighty God, I am Master Sankashan. Today I want to talk about nuclear fusion with the palladium elements. The simplification is allowed because the classical tuning points fortunately satisfy R is less than R in the high energy case. For very low energies, the full exponential must be used. Other considerations, such as the impact of positive ions on the screening potential as well as dynamic effects, can be introduced to the Colombo potentials as additional corrections, which was told in reference 48. For the purpose of this discussion, they will be considered negligible and fusion rates will be considered through the context of the constant screening potential VUE as introduced above. A more detailed expression for the screening potential given in the Sersky and his colleagues in 2016 in reference 49. UA is equal to e to the power of 2 cot TF is equal to 2e to the power of 3 divided by hp to the power of 1 divided by 3 to 3pm to the power of 1 divided by 6 square root of m star, where cot TF is the Thomas Fermi wave number, N is the electron density, and m star is the effective electron mass. In first approximation, the effective electron mass is the electron rest mass me. However, in some solid state environments, the effective electron rest mass is higher due to local electronic band structure changes that result from specific geometries. The two electrons of a gas phase hydrogen or deuterium a molecule correspond to the screening potential UA of the almost 25 electron volts reported theoretical UA values range from the 50 to 150 electron volt for different metals, which lithium at the lower range and palladium at the upper range. See figure 1 and also the reference 43. While theoretically predicted screening energies have been calculated for a variety of metals, it should be noted that the screening energies derived from experimental data based on observed fusion rates are higher than predicted values in reference 55. Experiments to determine screening energies have been carried out by multiple groups in 56, 57, 58, and typically involve low energy deuterium bombardment of different metal targets with concurrent measurements of resulting nuclear byproducts, for example, neutrons and charged particles for the same materials, where the theoretical screening energy range is given at 50 to 150 electron volts. The experimental screening energy range reported is 150 to 300 electron volt, figure 1, and beyond in the reference 51. In other words, experimentally observed fusion rates are substantially higher than expected if one were to only consider proximity and screening within the gamma model. The typical approach in the literature is to parameterize such discrepancies in and include them in the phenomenological correction factor or without understanding all aspects of them casually. The theoretical models for screening typically assume effects due to free electrons, which can begin to account for the large screening observed in low energy ion beam experiments. The screening energies predicted from such models are substantial for relative deuterium kinetic energy in excess of 1 kilo electron volt, but is much smaller at zero relative energy in reference 58. Note that the 1 second to the power of 2 electron orbitals, which are relevant to two deuteriums in close proximity, are unlikely candidates for acting as free electrons. It may be that an alternate mechanism is relevant in this context. A deuterium pair, for example, in the form of deuterium complex, see section 6. 0.21 proximity to the palladium atom can be imagined to undergo more complex dynamics, where both of the deuteriums tunnel into the palladium electron orbitals before tunneling through the Coulomb barrier between them. In this kind of scheme, there is a possibility of screening due to bound electrons at much higher electron density and therefore stronger screening. It will be possible to model this kind of screening with a special purpose quantum chemistry code that is constructed for or adapted to the problem. This would represent another mechanism for enhanced screening. However, this conjecture is yet to be explored in more detail. You see, we have a figure 1 which illustrates a reported experiment orange and theoretical as a TL screening energy values reproduced with permission from Hooper and his colleagues in 2008 by the reference 43. X-axis show atomic number from the 0 up to the 90, and y-axis is illustrating screening energy based on the electron volt. You see that in the experimental, by increasing the atomic number, we have a screening energy is increasing based on the electron volt. So I want to go through the quantum dynamics of nuclear fusion in condensed matter. As overview, nuclear fusion can be modeled in first approximation as a two-level system (TLS) undergoing a spontaneous transition from a highly metastable excited state to the ground state at a rate corresponding to what we can refer to as the fusion rate. In other words, an excited TLS or two-level systems, i.e., for example, fusion reactants, relaxes to its ground states, the fusion products. If the number of final states is large enough to be represented as a continuum of states, the so-called Golden rule can be applied to extract a rate as shown below in the reference 60. This is indeed the case in the conventional thermonuclear fusion picture, where the possible final state represents a continuum fusion product as a particle with momentum in all directions of space. The equivalence of modeling tunneling with the Van Sol-Kramers beryllium WKB approximations, the gamma factor approach, as discussed in section 3 and shown in more detail in section 6.3, and modeling spontaneous emission via the golden rule, as shown here, is explicated by Rajah in 61. The simplest Hamiltonian representation of TLS of two-level systems, HTLS, that relaxes from an initial excited state R to its final ground state F, is shown as H at two level of systems. This is a matrix says the first row is IV, the next row is V star F. Where V represents the coupling between the states I and M, a corresponding diagram is shown in figure 2. The described treatment of deuterium system as a two-level quantum system is discussed in greater depth of Hagelstein in references 62 and 63 and in section 5.1. Figure 2 illustrates essential features of a two-level system. An excited state positive is coupled to ground state minus, whereby the coupling is represented by V. A perimeter encompasses all interacting elements of quantum system, which in this case is only the two level of systems itself. Now consider the helium-4 and plus gamma channel of deuterium-deuterium fusion. The photon can be emitted in many angular configurations effectively, making the number of final states infinite and leading to irreversible dynamics. In reference 64, practically zero probability of reabsorption. In this case, the Hamiltonian matrix more accurately is a Hamiltonian golden rule, and you see we have a matrices as shown in equation 8. The transition rate tau per the golden rule from an initial state I to a continuum of final states F is as follows: tau I tends to F is equal to 2p divided by h absolute fhi to the power of 2, with the latter term taking on the value of fhi is equal to v almost e to the power of minus g, where the transition matrix element v between I and f is represented by the inverse exponential of gamma factor g, which represents the penetration probability. The small value of v represents the lab probability of the nuclear transition. This treatment results in an equivalency between the transition rate and the fusion rate for a two nuclear system, which their characteristics of the exponential probability distribution figure 3. Figure 3 illustrates a two-level system with a continuum of final states. When a TLS can relax into a near infinite number of final states, transition probability takes the form of a decaying exponential per the golden rule expressions equation 11. Here, the near infinite number of final states are represented by small differences in final state energies and in differences in the angular orientation of resulting photon emission. So you see, we have a time evolution in different areas, and also this plot, which is illustrating a state occupation probability in the y-axis, and when time passes, you see that state occupation probability will be decreases. Tau I tends to F represents a decay channel that is always available at the given rate in the two nucleus system. However, it is not necessarily the only decay channel if a coupling to a resonant or near resonant quantum system exists. Additional dynamics must be considered, specifically in the case of resonance with a receiver system, sometimes referred to as an acceptor system. Energy transfer can occur. See, for instance, the nickel quantum dynamics described in 65. Figure 4 shows a two-level system coupled to a resonant oscillator that allows for direct energy exchange between the two, resulting in Rabi oscillations between states. Positive 0 and negative 1 in the simulation is based on the quantum dynamics Python library QTIP and available at github.com/project dash idea slash two-stage quantum systems. You see, we have a time from the 0 up to the 100, and y-axis shows state occupation probability. This can give rise to complicated dynamics, including linear and nonlinear Rabi oscillations, where occupation probability oscillates back and forth between donor and receiver systems. Generic examples of receiver systems in this context include oscillators and additional TLS. The first approximation, the Rabi frequency, which characterizes the oscillation rates, depends on the coupling strength and due to the tuning between the two systems. It can be expressed as ohm Rabi is equal to square root ohm 0 to the power absolute ohm 0 to the power of 2 plus delta to the power of 2. Here ohm 0 represents the coupling strength, and delta is the tuning parameter defined as the difference in transition frequencies between the two systems. Delta is equal to omega system 1 minus omega system 2. When the two systems are in resonance, delta is equal to 0. The Rabi frequency reduces the coupling strength ohm 0, resulting in a maximum energy transfer between the states, bringing this Back to the nuclear fusion context, if a fusion transition can be grouped to one or multiple receiver nuclei acceptor nuclei with matching transitions, and if the transfer rate of the process is faster than the spontaneous decay rate, then there is an alternative fusion pathway. We will later see the ohm is a function of the fusion hindrance factor e to the power minus g, but also of other variables that can be used to increase the frequency. For a TLS coupled to an oscillator, a so-called Rabi Hamiltonian can be used to describe the dynamics. Hamiltonian Rabi is equal to h omega 0 the sigma z plus h omega r tau r plus v r to the power of t interactions plus all sigma s. Here h omega 0 is the transition energy into TLS. H omega is the energy in the oscillator mode, and V refers to the interaction between them. Sigma x, sigma z are Pauling matrices, and alpha and R are creation and annihilation operators. A resonant oscillator would correspond to the case where omega 0 is equal to omega. The time evolution of such a resonant system yields an occupation probability that the Rabi oscillates between the TLS and oscillator. See figure 4. While the above implementation illustrates what a coherent deuterium fusion tunnel could look like, an oscillator can be practically implemented at this time that can readily absorb the 23.85 megaelectron volt energy that would result from the detergence to the helium-4 reaction. However, a modified version of such a system can be implemented where another TLS with a resonance excited state such as another nucleus absorbs the release energy, and where a non-resonance oscillator mediates the transfer dynamics of the general case with many such resonant TLS or two level of system can be described which is so-called Dick Hamiltonian. Hamiltonian Dick is equal to h omega 0 sigma lower boundary j is equal to 1, and the upper boundary is L sigma s to the power of j plus h omega r to the power of t r plus v the omega sigma lower boundary is j r sigma x to the power of j r plus it. Here index j counts over n nuclei and corresponding interaction terms with the share oscillator mode. Time evolution for the specific case of two resonance two level of systems yields an occupation probability that Rabi oscillates, but this time between donor TLS and receiver TLS, where the oscillator merely mediates the transfer rather than fully participating in it. Figure 5. In such a case of non-radiative transfer, the mediating oscillator can facilitate the transfer of a large quantum of excitation, in our case 23.8 mega electron volt, without ever having to hold entirely of that energy itself, based on the references 68 and 6970. This is a critical point since many readers may intuitively assume that in such a context, the oscillator needs to be also able to fully absorb the energy quantum that are to be transferred. This is however not the case, as can be shown simply from the time evolving corresponding versions of the well-known Decay model as demonstrated in the Python notebooks hosted at the github.com/project IDA. Two-state quantum systems, the coupling between nucleus in that case is indirect, for example via the mediating oscillator modes, whereas the coupling from the each nucleus to the oscillator mode is direct. Example of oscillators relevant in this case are phonos and plasmons. Note that a key feature of such a decay model related transfer scheme is the acceleration of the transfer rate as a function of the number of participating systems. See section 5.2. When considering D2 as a donor system in such excitation transfer dynamic, two level of systems in the excited state capable of undergoing a D2 tends to helium-4 transition with its 23.85 mega electron volt transition energy. Then a resonance receiver system is needed as well as a share oscillator mode that both systems are coupled to a group state helium-4 nucleus offers a perfect resonance excited state via the helium-4 tends to D2 transition. However, in this case, the donor side D2 tends to the helium-4 transition and the receiver side helium-4 tends to D2 transition would remain within a closed system. For example, D2 helium-4 turns into helium-4 D2 accordingly. The process would be difficult to observe for a lack of clear reaction products, and it would be also likely still to slow to reach the observable range. See section 5.3 for corresponding rate estimates based on concrete parameters. A key reason for the comparatively slow rates despite current dynamics is the fact that the Coulomb barrier as a key hindrance to the involved transitions comes into the rate equation twice per transfer. Once on the donor side, D2 tends to helium-4 transition, and once on the receiver side, helium-4 tends to D2 transition. So, figure 5 illustrates the two large systems. Coupled share oscillator mode with resonant TLS states. The copper resonance two level of states allows for indirect energy exchange between the two TLS via the share oscillator mode, resulting the Rabi oscillations between states negative positive 1 and positive negative 1. The simulation is based on the quantum dynamics Python library quoted and it's available in github.com slash project slash ida slash two state quantum system. This is Thank you so much for watching my tutorial video until the end. Today is the third day of July 2026 times midnight. If there's any simulation, you can find it from my github.com slash master script, partial script, or software script. Also, you can see inside the this project simulation that was mentioned, Project IDA.